Okay guys, so we are back. I have to close it. Okay, can you see it? Yes? Okay. So now you saw that for the homogeneous part we had that, okay? So, but the poles or the roots of the system was a pair of imaginary roots or poles. So if I show it in the complex plane, this is complex plane because it's a complex number. Imaginary axis and the real axis. So they are located here, say here, plus omega n minus omega n. This is pure imaginary axis, plus omega n. By this kind of the roots or poles, we had forever oscillating system, right? Mathematically we proved. So theta versus time. Okay. So now you tell me your system is stable or unstable without any excitation or disturbance. Okay. Any idea? Yep. Whatever located at the left side of the imaginary axis means your system by itself is stable. Whatever located at the right side of the imaginary axis means your system by itself is unstable. Unstable. Whatever happens on the imaginary axis, as in the case we have, means that it's in the border of stability and instability. So that's why we name it as marginally stable system. Marginally stable system. See what I'm saying? Yes? Good. This is marginal stable system. It's not unstable, it's not stable. It's on the border of stability. So any system that has only pure imaginary roots or poles that we're gonna say later, your system gonna oscillate forever. Okay? See what I'm saying? So now we know that system by itself is marginally stable. We did the second part of our problem. But now we have to design controller. Okay? We have to design controller. On the other hand, if I want to plot block diagram that I'm going to do in details, block diagram after Laplace transform, okay? This is, we name it plant, just for introduction. This is plant. We name, its technical name is plant. Plant can be car, can be airplane, can be pendulum, can be robot, can be the room. So you saw that this was differential equation. Theta double dot linearized is omega n square theta minus x double dot, right? This is your plant. This is dynamics of a plant. Now you are adding a u or torque. U means control signal. U plus u on the right hand side. So but this system is under this, guys, simply under, oh, let me do this because I want to make this happen. This is u. We're going to control it. I'm going to control the position of this pendulum, the angle of this pendulum, theta m, and this is disturbance of the system, x, that came in the form of x double dot acceleration. So this u okay, U is being added, okay, but minus this what? This this x double dot. That's right. You see what I'm saying? So now, if you do that, you're gonna have U minus x double dot here, and this goes here. Get here. This is operator of sum operator. In the Simulink in the MATLAB we have it. Plus, minus. If a signal comes here, A, another signal comes here, B, the output is A minus B. Exactly you see here, that's right. So your function is to design this controller to reject this disturbance and keep, for example, the angle of the pendulum at 45 degrees. And you ask me where this come from? From the controller unit. C, we name as C. We name this open loop G, open loop transfer function of the plant, G. I'm going to introduce later. I'm just giving you the big picture of the course. See what I'm saying? Yes, guys? So, and now you're going to tell me, can I delete this one here? Yes? Okay. Yeah, okay. Now you're going to tell me, okay, what is that, this desired angle that you want to, this desired, this D that you're going to see in this chord means desired angle that you want to keep. Despite of this disturbance you are applying to the system, where is that in the block diagram? So you're going to have this. You're going to you want to keep this theta D, that is going to be pi over 4. This being an operator here, okay, is plus, please plot this in your notes, okay? So when you apply controller, being affected by this disturbance, going to the system, the system go solve the differential equation, okay, and give you real value of the angle. This real value I'm feedbacking, the name of this loop is feedback. I'm feedbacking to the system to be compared with the desired value of the angle. Are you following me? Yes? So, and a signal comes out of here, guys. A signal. What's the name of this signal? This signal? E, error signal. Between, is difference between your desired angle of the pendulum minus the real angle of the pendulum. This E goes to control unit. And we are designing the controller based on this error signal. I'm going to teach you later how. And this loop continues until this theta R becomes equal to how much? Become equal to how much? 40. Yeah. Means this continues, this loop, this feedback loop, this we are saying feedback loop is being carried out until error signal becomes how much? Error signal? You tell me. When theta R equals to theta D, how much is E? 0. And you as control engineer in NASA, you as control engineer in Tesla, you as control engineer in the car manufacturing companies, you as control engineer in wherever you are as control engineer, your only function, one of the most important function to make this happen, make error signal to how much? 0. Now that you are sitting in the room, there is an AC box. That AC box is this control unit. When you set it to 80 Fahrenheit, That 80 Fahrenheit, look at here guys, is your desired temperature. That controller generates heat, and by sensors, okay, in the feedback loop, let me do that because I want to give you a very clear picture of everything. In the feedback loop, there is sensor always, sensor, like as the temperature sensor. We are showing with the H. I'm gonna explain this later. This controller sends some command, okay, to the dynamics of the room temperature that I'm gonna explain later. It's gonna give you some real temperature out. This real temperature is being sensed by sensor, sending to be compared with the desired what? Temperature. You're gonna have error signal going to the controller, and this loop continues until your desired temperature equals with your real temperature. You got the picture? Yes? Yes, guys? Great. Okay. Now you got the big picture. Suppose that now you are controlling a temperature room. So what can be disturbance for the temperature control problem? How? Just give me a real example. Exactly. Exactly. Someone in the winter opens the window. Okay? That's a disturbance that you want to reject from the system. See what I'm saying? Yes, everybody? So can I go to the next page? Okay. So for any moving system that we are working as engineering this planet, or sending satellites by Tesla, or whatever that you are doing that is moving, okay, the whole story is this. You're saying X desired plus minus goes to control unit C, goes to plant G, goes to real output of the system, is being feedback and sensed by sensor H, is being compared with the desired input, makes you error signal. And here is U, control input by the controller. If there is no disturbance, if there is disturbance, fine. You can add a disturbance. Let me do that. G, sure. Plant, open loop transfer function. I'm gonna explain after the Laplace transfer. So you can have disturbance with capital D, that it can go to the system, okay, and oh my god, and I have to delete this. This gives you U is being summed by disturbance, plus or minus plus, and this goes to the system. Okay, let me make it more clear, because this is very let's change the color. Plus, here we go. So this is your plant, this is your controller, this is your sensor, these are desired input that you want to follow, real output of the system, error signal, and the disturbance of the system. Clear, guys? Yes? Okay, so based on whatever I said, we did step 1. We developed differential equation nonlinear. We linearized on the equilibrium point. We judge the stability of the system based on the internal dynamics of the system or homogeneous solution of differential equation. For this specific system, we saw that, okay, we have a pair of pure imaginary roots or poles, so your system is going to oscillate forever. And then we added controller, but you don't know how to do it because it's a long way that we go there. Okay? The whole semester. But now, let me go to the MATLAB and simulate this system. Theta double dot plus omega n square theta is minus x double dot. I want to make a simulation in MATLAB of this system with disturbance that we have and without controller yet. We're still lacking controller, only with disturbance. Without controller, we don't have it yet. Okay? So for those of you had vibration with me, probably you know how to do it. For those that you don't know, I'm teaching here because we're gonna deal with this a lot. State space equation. State space equations. State space equations. Okay. In state space equations, you have to define state variables. State variables, saying that variables that they are indicator of the system state. For this problem, system states are the angular position of the system, and angular velocity of the system. So we are defining a state space exactly as I'm doing in MATLAB. M1 is theta, and the M2 I'm saying is theta dot. I'm going to transfer exactly this to the MATLAB. Okay, and M1 and M2 names are state variables. These are technical names. So having the time derivative from the both sides, you have dm1 means time derivative of this equals to theta dot. And what is theta dot? You let me know. What is theta dot? No, look at here. What is theta dot? Yes, it's equals to m2 because I'm going to type this in MATLAB exactly. Okay. Now here, dm2 time derivative of that is theta double dot. Theta double dot from this equation we can find it. Look at here. Theta double dot is minus x double dot minus omega n square theta. Let me call this, as I told you, D. D stands for, as I told you, no, this D. Disturbance on the system. Okay. Minus omega n square. What is theta based on the state variables? Look at here. What is theta? Yes, m1. So it's gonna be minus d disturbance minus omega n square m1. So now, for the first time in this class, we derived state space equations. dm1, I'm gonna exactly type in MATLAB, is m2. dm2 is minus d disturbance minus omega n square M1. And I'm going to type exactly this inside MATLAB. Okay? But before going ahead, guys, when I say state variable is valid for your car position. So when I'm talking about your car, its position is a state variable, its linear velocity is a state variable. When I'm talking about the pressure of a tank, its pressure is state variable, its rate of the pressure is state variable. When I'm talking about temperature of the room is the first state variable and T dot is second state variable. Whatever you say, whatever that you are trying to control. Here, only theta, angle of the pendulum, and theta dot were our state variable. Clear, guys? Yes? Okay. But before going to the MATLAB, can I go to the next page? Yep. So, this was our problem, guys. This. A moving pendulum, M, L, and theta. So your system must start from some initial condition. In dynamical system, this is very important. Initial conditions. Initial conditions. For example, you say, you know what? I'm going to start my system from here. Here is 45 degree because you have two state variable, angle, theta naught state and colon and initial value of the velocity, the dot naught is 0. I'm just giving some numbers. You're gonna tell me no. You know what? I want to have the initial conditions in MATLAB exactly from here, 0 and 0. Another one says no. I want to have it at this position. Say minus pi over 4 and 0. See what I'm saying? Initial conditions for solving differential equation even in your undergraduate level course is very important. So is in MATLAB. Clear, guys? Yes? So, now, as we defined here, please go here, yeah. We have a disturbance. I have to define in MATLAB code. I'm saying x of t that is moving for the base is a periodic term, sine of t. Look at here, I'm saying this moves like this. Ding, 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 ding. This is disturbance of the system. So, x dot, because your d is x double dot, x dot be cosine of t from mathematics, and the x double dot gonna be minus sine of t. So in MATLAB code, we have to, instead of t, we have to with minus sine of t. See what I'm saying? Yes? This is disturbance of the system. Like, assume that you want to dance. I'm not joking, this is serious. Because this is the simplified model of your leg, right? And your hip joint, in the dance fashion, it goes back and forth. And now you want to keep the angle of your hand at the 45 degree. This is a control problem, man. Like as Michael Jackson. Okay? See what I'm saying? Yes? Everybody? Okay. So now let's go to the MATLAB. Now it's showtime. Okay, so MATLAB. Okay. Okay, guys, please come up. For God's sake. Okay, guys, give me a joke until that MATLAB loads. Hello? MATLAB? Oh, okay. So, okay. So, what you're gonna do, you have to open M file. Do you see the MATLAB screen? Yep. So, you open M file, new script, and then for solving the ODE, you have to say function. You have to do function. DM, as we did exactly DM. I'm saying control class pendulum, any arbitrary name. Now you have to design the variables. Is time, MATLAB understand, and M. Remember, M was our state variables. Then I'm saving this. We're in ME530. This name, guys, must be exactly with this name here. If they are different, MATLAB gonna give you syntax error when you're running that. This is M file. See, now the name changed. Control pendulum. Then I'm generating a space. DM is equal to zeros 2 and 1. Why I'm saying 2 and 1, guys? Why I'm saying that? Because we have two state variables. Look at here. I'm just putting here zeros. Do this. 2 zeros. If you have 3 state variable, you have to have 0, 3 and 1. If you have 10 state variable, 10 and 1. Okay? So now what I'm gonna do, I'm gonna define omega n of the system. Omega n. Why? Because exactly I have to put it here. You see that? Yes, guys? Hello? Okay. So omega n of the system, I'm putting, I don't know, 5 radian per second. I'm commenting it is in radian per second. This is how you comment in MATLAB. Okay? So percentage, and you write the comment. Then I'm saying D, disturbance of the system. It was minus sine, as we derive together, T, time. See, I'm exactly copying here. Here we go. Here. Minus D, our D was X double dot. See here? Minus sine omega. Let me see. So minus, okay. So because it is, I'm saying your D is, your X is, so minus is plus. So here gonna be, see, minus, this minus, in this minus gonna be plus. So it's gonna be sine of D. Not, okay, let's just keep it like that. Okay, it doesn't matter. So your D is that. Okay? Your D is that. So now I'm typing DM1 is M2. You see your notes? Exactly, I'm typing. DM2 is minus D. See here? Minus D. Minus D. And we define D as minus sine T. And minus omega n squared. This is how we write square. Multiplied by M1. Anyone agree? Yes? Yes, guys? Okay, so, and I'm saving this. Now I have to generate another M file for solving this differential equation. I say uh, uh, time, I want to run this simulation from 0 with a step size of 0.1 second, 0.01 second to 10 seconds. You know what this does? Look at here. Here we go, guys. Yeah, I'm just showing it. Look at here. I'm just showing. Look at here. See what it does? Let me show you. Starting from 0, 0.01, 0.02, 0.03 until 10 seconds. See what I'm saying? Yes? Now you can change it to 0.001. Okay? 001. Make it your time step much smaller. See what I'm saying? Then I'm saving this to solver. How? I'm just putting saying solver, any arbitrary name, control moving pendulum, whatever. Okay, I'm just saving that. See, it changed. Now this is the command. I'm saying the whole time and the whole state variables equals to ODE solver, ordinary differential equation solver number 45. Just you put it, don't ask me why, because we have different solver, because OD50, OD15S, OD113, this is nothing in level, just 45, it works for you, okay? At means go and call another M file. This, I'm calling this M file. What was that? Contend, okay? Now time, now initial conditions, I'm saying 45 degree and 0. Okay, here we go. Okay, so let me clear the workspace. With this command CLC, I'm clearing the workspace. If I run this, guys, look at here, to debug our code. See, it solved our problem. Now bear with me, because I'm going to teach you here, guys. Okay. How many state variable we had? You tell me. How many? 2. So the first column is all state variable 1. State variable 1 was the angle of the pendulum, right? Yes? So, and the column 2 is the angular velocity of the pendulum in 10 seconds. See what I'm saying? Yes? The column 1 is the angle of the pendulum. Column 2 is the angular velocity of the pendulum. Now, having those, I'm plotting that figure based on disturbance that we had to the system. Figure 1, understand, this is the command in MATLAB. Understand what's the meaning of the figure. It's like talking with MATLAB. Plot, it understands. Total time, T. See, this total time, T. And now the first state variable. Because, guys, look at here. All of you look at here. If I want to plot all the angles, I'm going to say this command. This and the first column. This means all rows, this means, and the first column. See what I'm saying? This is how we write in MATLAB. Multiplied, because this is in radian, I want to make it in angle, 180 divided by pi. And I'm saying, please do it in the blue color. And I'm saying, line width, make it much thicker. Line width of 2. Okay? See what I'm saying? Now let me run it. Here we go. We started at 45 degree And based on, you see, based on the disturbance, even the amplitude fluctuating. See guys, do you see that? Yes. Okay, now you can grid it, and now, okay, and now like this. See, you can increase the time. I want to see what's the effect of that. 20 seconds. See, now you can see the fluctuation based on the disturbance. See what I'm saying? Huh? So now your function, because the system was marginally stable, system was oscillating, but if it was not disturbance, all of you look at here, the amplitude was exactly like this, very smooth and uniform. But this disturbance caused this oscillation in amplitude. But your function is to keep that angle at a 45 degree, not even marginally stable. So now we have to go to control. See what I'm saying? Okay. Yeah, sure. By the way, when I'm done with the coding, I'm gonna upload it to Canvas. Okay? Clear? I'm not done because I have to do many things on this. The next class I'm gonna work on this. I'm gonna expand the work. So suppose that the original, guys, now I'm increasing the amplitude of the disturbance a lot. I'm saying disturbance is 3 sine t. Here it's gonna be 3 cosine t minus 3. See what I'm saying? I'm increasing the amplitude of the disturbance. So I'm saying it's 3 here. Here we go. Okay, let us see what happens. Here we go. Oh, see? See what I'm saying? And now it's getting close to 60. You are making the disturbance much larger. See what I'm saying? Yep. And now we can even increase, say, okay, you know what? I'm going to start with the P/4 and -1 radian per second as initial velocity. You have different profile, obviously. Okay. So yeah, I'm gonna stop it here because it's too much, because I want to work on this a lot. Okay. And then we're gonna work on the Laplace transform, and we're gonna go out from there. Okay. Okay, guys.